Hello, welcome to my Lightwave Systems project. Today we'll be talking about the Terabit Intra-Datacenter Photonic Fabric technology. Okay, okay. So what is the vision for this project? Currently in data centers, we are seeing a bottleneck when it comes to performance, and that bottleneck is coming from the interconnect between our compute cores, like our GPUs and CPUs, and our memory. We've learned about this in our class, and we're seeing it in the real world that this is what's really limiting our hyperscale data centers of today. So what we're proposing here is a advanced photonic solution that will replace copper and serial deserial electrical networks with integrated silicon photonics technology. Our goal is to provide terabit per second per node. This will do some work to alleviate the bottleneck that we're seeing today. And it's known that silicon photonics can be up to 10 times as efficient as electrical networks. And with this, it will really help to meet the demand that we're seeing for high memory transfer applications such as AI and high performance computing. So let's talk about the current state of the art for optical interconnect technologies. Most common, what we're seeing today in data centers are pluggable optic solutions, which have a PIC inside, but are also being interfaced with electrical serial deserializers. These are things like the QSFP and OSFP, quarter and octal. But the problem with these is their bandwidth is in the range of hundreds of gigabits per second per node. And this is good. It's better than what we were using with the electrical, but it still is not as good as what we could achieve with um, an integrated solution. What we're seeing come out recently are things like co-packaged optics. So now we're having um, silicon photonics integrated on a chiplet with the compute cores, um, but these are tricky to manufacture, and these are still in the early stages of development. And those are the two main things we're seeing today in terms of high capacity interconnecting solutions. Um, yep. So, what are the limitations with what we're seeing today? It's mainly the bandwidth constraints. Although these are way better than um, purely electrical interconnects, it's still not quite enough for the capacities that we're seeing with modern workloads. And also, because of the interface with electrical serial deserializers, this incurs a large energy overhead that a system that was purely photonics would not incur. And because of the difficulty with fabrication and alignment, thermal stability, these things are hard to scale um, past maybe single node or 1 unit per node, thus limiting the bandwidth even further. So what we're proposing um, is a fully integrated solution that is removing any dependence on electrical interfaces using a direct silicon integration, something like the co-packaged optics. Um, we're hoping for a dramatic increase in a bandwidth over terabit per second range. And looking at something like less than 1 picojoule per bit, this will provide over a 10 times improvement compared to what we have today, right? These are the hopes, and in the next slides, we'll discuss the technical details on how we plan to achieve this. So in this slide, we'll be talking about the architecture of the design of the TIPF. We're planning to use a micro ring resonator based switching architecture. The central idea is to use arrays of integrated MMRs as wavelength selective switches, so we can dynamically route traffic in the optical domain, right? So we've seen this in class where each MMR can act as a tunable filter. When we shift its resonance, we can selectively drop or pass specific wavelengths from a signal traveling through a waveguide, right? So let's talk about the micro ring resonators for a bit. They're small silicon circles, typically something like 5 to 20 microns in radius, and they're evanescently coupled to linear waveguides. We saw this in Lightwave devices last semester as well. They allow selective coupling of specific channels depending on the ring's resonance, kind of acting like as a filter for specific frequencies. Because of their small size and low power, they're good for dense integration on a chip, and they used to be really only for academic purposes, but we've seen recent industry leaders start adopting them in their interconnect technologies as well. Okay, so we need to tune them actively. We're planning to use either thermo-optic tuning or electro-optic tuning. Both are methods to change the refractive index of the material, depending on foundry costs and what's available during prototyping and adoption stages. That will kind of determine which approach you will need to take. Okay, and as for the fabric, we're planning to route them through a interposer, which is kind of like a backplane on the chip. They are laid out like electrical traces, but with higher density and no crosstalk, because that's kind of the nature of the waveguides. So this waveguide layer will replace traditional electric PCB routing. Okay. Let's talk about some of the design parameters for the MMRs we're using in our fabric. We're planning to use a standard silicon on insulator platform where we have 220 nanometers of top silicon. That's common in photonic foundry PDKs. The ring radius is depends. It could be between 5 to 20 microns. Smaller rings are save on area, but they increase bending loss. So we plan to select radius based on a trade-off between area, low insertion loss, and required FSR. Okay, so what is FSR for this design? It will be typically around 1 to 200 gigahertz, and this is going to determine how many channels we can pack into the WDM grid without interference. So we're aiming for a Q factor of between 5 to 20,000. Higher Q is a narrower bandwidth and lower loss, but it also increases sensitivity to fabrication and thermal drift, right? So each microring is designed to have less than 0.5 dB insertion loss, which is critical. And we can come back to the tuning. Thermo-optic is more precise, but it's power hungry. Something like 20 microwatts per ring. But for fast reconfiguration, we can use the electro-optic tuning via carrier depletion or injection, and this will help us save time and energy. And in practice, we'll probably use both thermal for coarse alignment and electro-optic for fast dynamic switching. And at the fabric level, how are we going to configure these MMRs? So we're planning to arrange them in a large-scale switching matrix that is going to enable this wavelength selective routing between nodes. We are looking at building a layer using cascaded microring arrays, and each input-output pair can be dynamically mapped to a specific wavelength by tuning the appropriate rings. So each section can talk to any other member of the other matrices. So we chose 8 by 8 blocks because it's scalable and it can reach higher port counts such as 64 by 64 or beyond. And on the silicon photonic interposer, we'll use single mode waveguides with loss of around 0.5 to 1 dB per centimeter. That's to avoid excessive crossing and bending loss. And to couple with the interposer, this can be either done with grating couplers or laterally with edge couplers, with insertion loss kept below 1 dB per interface. And for lasers, instead of integrating lasers on chip, we're planning to use continuous wave lasers located off package for better thermal isolation and power efficiency. So besides the tuning of the rings themselves, we can also talk about how we can use SDN, a software-defined networking controller. This will basically be the layer that sits on top of our resonance tuning system. This will be sort of at the link layer in the network protocol, if you can use that analogy, maybe a bit higher than that, and we'll try to build APIs for orchestration level integration and low-level SPI or I2C interfaces for tuning controls. And of course, we'll have to integrate photodetectors for power level monitoring. This is to maintain link quality, detect faults, and measure optical power levels at key points. So let's talk about the performance targets and how we plan to get there. Right, so we talked about how we're using two different kinds of tuning mechanisms. This is going to help for coarse tuning and fast switching. Power is very low on a switch event under 0.1 picojoules is achievable when using electro-optic control. And to ensure high reliability, we'll also have redundant wavelength channels and alternate ring paths in the switch fabric. And in case of a device failure, we should be able to reconfigure routing paths in under 10 microseconds using pre-characterized standby rings. Okay. And all the components we're planning to use CMOS compatible processes, making them manufacturable at existing silicon foundries like TSMC or Intel. And for prototyping and scalability, I think right now companies are already looking at this first phase. We've seen some industry leaders demonstrate something on this level, and maybe some glimpses into the rack level fabric, but we'd like to accelerate this and maybe push to be in the data centers within the next 5 years. That would be a great goal, but the current timeline, it's looking like it might be in the next 7 years, but it would be good to have them in the next 5. So the specialized applications that this will be useful for, of course, AI models and training need high memory transfers, high capacity memory transfers. That's how they work, and this will help with that a lot. And this is going to be very useful for these specialized high performance computing environments. And I'm kind of running out of time here, so I'll speed up. But yes, the key barriers are going to be it's very expensive to research and design in the beginning, and we'll need automation like an EDA for layouts and RTL sort of architecture to a GDS flow is going to be really useful for us to have. And we're going to need to find a way to integrate it quickly with existing technologies. But what is it? What is on its side is that there is high demand and standardization efforts coming from major silicon foundries and government incentives. Okay, so like we discussed, the interconnect is the bandwidth, and we're planning to use microring resonators to build a switching fabric to solve that problem. And hopefully within the next 5 to 7 years, we're going to be looking at them already within data centers, working on AI training workloads and high performance computing environments. Okay, thank you.